Hello friends, welcome to lecture series on multivariable calculus. So in the last lecture we have seen what chain rule is and how can we apply chain rule on multivariable functions. Now we will see some more properties of chain rule. Now let us suppose function x y, function of two variables, be differentiable and the equation f x y equal to 0 defines y implicitly as a function of x. Then so here we are taking w as a function of x and y and which is equal to 0. We are assuming that this function is a differentiable function and we can express y implicitly as a function of x. Now differentiate both sides with respect to x. So what we will obtain? So it is again dw by dx will be 0 of course. So this implies, now what will be dw by dx from here? Now f is a function of x and y, okay. So we can apply a chain rule here, it is del f by del x into dx by dx plus del f by del y into dy by dx equal to 0. Because we are having two unknowns x and y here, okay. We are having two unknowns x and y and we are differentiating with respect to x. So with respect to x we are differentiating, okay. So dx will cancel out and this is implies, or it is 1. So it is del f by del x plus del f by del y into dy by dx is equals to 0 and this implies dy by dx is equals to minus fx upon fy should not equal to 0. So if you want to compute dy by dx directly if f is known, so simply we can use this expression negative of fx upon fy, that is differentiate partial respect to x divided by differentiate f partial respect to y, okay. So see some problems based on this. Suppose f is, suppose it is x raised to power y plus y raised to power x is equals to alpha, okay, where x and y are greater than 0 and alpha is any constant, okay. Now we want to compute dy by dx for this equation, we want to compute dy by dx. So how can we do that? So we can use this expression, basically we can let f of xy as x raised to power y plus y raised to power x minus alpha equal to 0. Now we know that dy by dx is nothing but minus of fx upon fy, provided fy should not equal to 0 of course, okay. So from this expression we can get back to find dy by dx which is negative of. Now fx means differentiate partially with respect to x. So differentiate this expression partially with respect to x. So keeping y constant, so it will be y x raised to power y minus 1 plus y raised to power x ln y, okay, upon, because we are treating y as constant. Now fy, we are differentiating this expression partially with respect to y keeping x constant. So it will be x raised to power y ln x plus x y raised to power x minus 1. So this will be dy by dx. So simply using this expression we have solved this problem very easily. We have find out dy by dx very easily using this formula, okay. Now the second problem is x e raised to power y plus it is sin xy plus y minus ln 2 equal to 0, okay, and you want to compute again dy by dx. So you can let f of xy as x e raised to power y plus sin xy plus y minus ln 2 equal to 0 and dy by dx will be given as negative of fx upon fy, which is equal to negative of. Now, partial derivative of this f with respect to x. So, it is e raised to power y plus sin theta is cos theta and theta again, that will be with respect to x, that is y plus 0, okay, upon. Now, fy means partial derivative of this f with respect to y. So, it is x e raised to power y plus cos xy into x, okay, and plus 1 of course, because derivative of this is plus 1, partial derivative of this is plus 1. So, this will be dy by dx, which we can compute easily using this result. Okay. Now instead of two variables, suppose f is a function of three unknowns x, y and z, where z is a differentiable function of x and y, and at points where fz is not equal to 0, we can easily say that del z by del x is given by this expression and del z by del y is given by this expression. How we can obtain this expression? Now, here f is a function of x, y, z, which is equals to 0. Now, you differentiate partially with respect to x. Okay, so that means you differentiate with respect to x. So, that will be del f by del x into dx by dx plus del f by del y into del y by del x plus del f by del z into del z by del x equal to 0. Okay. You differentiate partial respect to x, you can write d here or del here. Okay. Now, this implies del f by del x, this is 1. Now, y and x are independent. Okay. So, del y by del x will be 0. So, this will be 0 plus del f by del z into del z by del x equal to 0, and this implies del z by del x will be minus fx upon fz, provided fz is not equal to 0. So, that is how we can obtain del z by del x, the first expression here in this PPT. Okay. Now, if you want to compute del z by del y, so similarly you can differentiate here partially with respect to y. So, it will be del f by del y into del y by del x plus del f by, okay, you have to differentiate partially with respect to y. So, it is x and here it is y. Okay. It is del f by del y into del y by del y plus del f by del z into del z by del y, because you are differentiating partial respect to y, both the sides. Now, again x and y are independent variables. So, this will be 0. So, and this is 1. So, this implies del f by del y plus del f by del z into del z by del y will be 0, and this implies del z by del y will be minus fy upon fz, provided fz is not equal to 0. So, that is how we can simply obtain del z by del y. Suppose we have this problem, find the value of del z by del x and del z by del y at 1 1 1 for this expression. We can obtain these values directly also, and we can use these formula also to find out del z by del x or del z by del y in this problem. What is the expression? Equation is x cube plus, it is x y plus y z plus y cube minus 2 equal to 0. Say it is f, and you want to compute say del z by del x. So, it is negative of, just now we have proved that it is minus of fx upon fz, fz should not equal to 0. So, what will be fx? Differentiate this partial respect to x. So, it is it is y, okay, in the numerator, upon with respect to z, it is 3z square plus y, okay, and at 1 1 1 it is at 1 1 1 it is minus 1 by 4, okay. You can simplify this directly also, differentiate this respect to x partially. So, z is a function of x and y. So, it is 3z square into zx plus, from here it is y, plus from here it is y into zx, because y is independent of x and it is equal to 0. So, this implies zx is minus y upon 3z square plus y, the same expression, okay. Similarly, we can compute del z by del y also at point 1 1 1. Now, come to some more problems based on chain rule. Say w, which is a function of x minus y, y minus z, z minus x is differentiable, then we have to show that fx plus fy plus fz equal to 0. This we have to prove, okay. So, how can we prove this? So, let u equal to x minus y, v equal to y minus z, and w equal to z minus x. So, this w, okay, this is w and this is also w, you make it you make this as capital W, okay. So, now this capital W will be f of u v small w. Now, what will be del f by del x? Now, this f is a function of u, v and w, and u and v, w are again function of x by z. So, that will be del f by del u into del u by del x by chain rule, del f by del v into del v by del x plus del f by del w into del w by del x, and that will be f u into del u by del x from here is 1. So, it is 1 plus del f by del v is del v f v, and del v by del x is 0, no x is here, plus del f by del w is f w into del w by del x is minus 1. So, it is f u minus f w. Now, similarly, if you compute del f by del y, it is del f by del u into del u by del y plus del f by del v into del v by del y plus del f by del w into del w by del y, and which is equals to, it is f u into del u by del y is minus 1 plus it is f v, del v by del y is 1, del y is 1 plus, and del w by del y is 0. So, this is 0. So, this is minus f u plus f v. Now, if we compute del f by del z, it is again del f by del u, which is f u into del u by del z, which is 0, okay, plus f v into del v by del z, which is minus 1, plus f w into del w by del z, which is 1. So, it is minus f v plus f w. Now, if you take the sum, if you take f x plus f y plus f z, sum of these three, so it is f u minus f w plus it is minus f u plus f v, and it is minus f v plus f w, and this we cancel with this cancel with this cancel with this, which is equal to 0. So, hence we have proved. Hence the first question we have solved. Now, the second problem. Okay. Suppose now second problem is z is a function of x and y, okay, and x is equal to u cos alpha minus it is v sin alpha, y is a function of again u and v, it is u sin alpha plus v cos alpha, okay, as given in the problem. So, alpha is a constant here, where alpha is a constant. So, x is a basically function of two unknowns u and v, and y is again a function of two unknowns u and v. Then we have to show that del f by del u whole square plus del f by del v whole square is equals to del f by del x whole square plus del f by del y whole square. So, let us try to compute this. So, what is del f by del u? It is del f by del x into del x by del u plus del f by del y into del y by del u, okay, by the chain rule. So, it is f x into del x by del u is cos alpha plus f y into del y by del u is sin alpha. Now, del f by del v is again f x into del x by del v, del x by del v is minus sin alpha plus f y into del y by del v is cos alpha. Now, if you take f u square plus f u square, this will be equals to square and add both these equations. So, what we will obtain? This square is f x square cos square alpha plus f y square sin square alpha plus 2 f x f y cos alpha sin alpha plus f x square sin square alpha plus f y square cos square alpha plus, so it is minus 2 f x f y cos alpha sin alpha. So, basically I have square and add both these equations, we obtain this expression, these two cancel out. Now, this is when you take f x square common, it is sin square plus cos square, which is 1. Again it is when you take these two common, it is cos square alpha plus sin square alpha, which is again 1. So, it is equals to f x square plus f y square. So, we have proved this problem, we have proved this equation, okay. And the next problem now, which is of involving second order partial derivative, let us try to solve this. Show that if w is equals to f of u and v satisfy the Laplace equation f u u plus f v v equal to 0, and if u is given by this and v is given by this, then w also satisfy this expression, I mean Laplace equation. So, let us try to prove this. So, here w is a function of u and v, and it is given to us that f satisfy Laplace equation, that is f u u plus f v v equal to 0, it is given. Now, u is a function of x and y, which is given as x square minus y square by 2, and v is again is a function of x and y, which is x into y. We have to show that w also satisfy Laplace equation with respect to x and y, that is to prove, we have to prove that w x x plus w y y is equal to 0. So, let us compute del w by del x first. It is, so del w by del x is, by the chain rule, it is del f by del u into del u by del x plus del f by del v into del v by del x, which is equals to f u into del u by del x, from here it is x plus fu into del v by del x, from here it is y. Okay. Now we have to compute del square w upon del x square, which is this term. Similarly, we can compute del square w upon del y square. Okay. Now how can we compute this? This is del by del x of wx, which is del by del x of wx is x fu plus y fv, this expression. Okay. Now you differentiate here with respect to x partially. First, as it is, derivative of this with respect to x, plus second as it is, derivative of this, plus y is independent of x. So, y is common, y comes outside, and it is del by del x of fv. Okay. Now, so wxs will be given as, now it is, now you have to apply chain rule for fu, because fu is a function of again x and y. F is a function of u and v, and u and v is a function of x and y. So you have to apply chain rule here, it is x into, so you can break it here, it is del by del u of fu into del u by del x, del by del u of fu into del u by del x. Okay. Del by del u of fu into del u by del x plus del by del v of fu into del v by del x, because both involve function of x, plus fu, which is this term, and plus y times, again you have to apply chain rule here, it is del by del u of fv into del v by del x plus del by del v of fv into del v by del x. Oh yeah, it is del u by del x, it is x into, now it is fuu, now del u by del x from here is again x plus it is f uv into del v by del x, from here it is y plus fu plus y into it is f uv del u by del x, del u by del x is x plus f vv into del v by del x is y. So this is what we are getting as del square w by del x square, which is x square f uu plus y square f vv plus 2xy f uv plus fu. Now similarly, we can compute del square w by del y square. So let us try to compute that also. So first del w by del y, it is del f by del u into del u by del y, which is minus y, plus fv into del v by del y, which is x. Now del square w by del y square, which is del by del y of wy, which is minus y fu plus x fv, which is, you apply a product rule here, it is minus of first as it is del by del y of fu plus second as it is derivative of first plus x del by del y of fv. Okay. Now it is minus y times, now you have to apply chain rule here again, it is del by del u of fu into del u by del y plus del by del v of fu into del v by del y, minus fu remain as it is fu plus x times, again you apply chain rule here because fu is a function of x and y. Okay. So, how can we do that? It is del by del u of f v into del u by del y plus del by del v of f v into del v by del y. Okay. Now, you can simplify it, minus y, it is f u u, del u by del y is minus y plus it is f u v, del v by del y is x plus minus f u plus x times it is f u v, del u by del y is minus y plus it is f v v and del v by del y is x. Okay. Now, when you add the two terms, I mean del square w upon del y square plus w x x, when you add both the terms. So, from here you are getting, okay, let us simplify this first. This will be equal to, it is x square f v v plus y square f u u plus it is minus 2 x y, yeah, it is minus 2 x y f u v minus f u. Now, it is w y y. Okay. Now, when you add these two, it is x square plus y square times f u u, x square plus y square times f v v, this cancel with this and this cancel with this. So, we are having w x x plus w y y as what we are having, w x x plus w y y as x square plus y square times f u u plus f v v, and this is equal to 0, which is given to us. So, it is 0. So, we have proved. Okay. So, that is how we can apply chain rule for if we are involving second order partial terms, partial derivatives. Okay. Now, it is also important to mention in the problem that which variables are dependent and which variables are independent, because sometimes if it is not given to us, so answers may be different. For example, suppose you have to solve this problem. For example, z is a function of w is and z is okay. So, here it is not given that which variables are independent and which variable is dependent, and we have to compute del w by del x. Now, since del w by del x is to be computed, so from this expression it is clear that x is an independent variable and w is a dependent variable. Okay, it is clear that from this expression we can easily see that w is a dependent variable and x is an independent variable. One thing is clear, for other variables z and y, okay, z and y, we are not knowing which variables are dependent and which variables are independent. Okay. Because we can also write y square as z minus x square. So, if you make this chart, for example, dependent variables and independent variables, from here w is dependent and x is independent, it is clear. Okay. Now, we have two possibilities. What are the possibilities? May be possible that y is independent and z is dependent, or we may have z as independent and y as dependent, because we have one expression in x, y and z. So, of course, one variable will be dependent, other two are independent, definitely. So, two variables will always be independent. Okay. So, these are two possibilities which we are having. Suppose we are opt for the first possibility, this is first case, this is second case. Now, for the first case, when we are taking w and z as a dependent variable and x and y as independent variable. So, what we have to compute? We have to compute del w by del x for the first case. So, del w by del x for the first case will be, now we differentiate this expression partial respect to x, keeping in mind that z is a dependent variable, these are the dependent variable and these are independent variable. Okay. Now, when you differentiate partial respect to x, it is 2x plus. Now, y and x are independent. So, partial derivative of y with respect to x will be 0 plus. Now, z is dependent on x and y. So, it is 2z into zx. Okay. And from here zx is 2x. So, it is 2x plus 2z into 2x from here. So, it is 2x plus 4xz and z is x square plus y square. So, it is 4x cube plus 4xy square plus 2x. Now, let us compute for the second case. Okay. Now, for second case, for the case 2, del w by del x. Now, for second case, we are taking w and y as dependent variable and x and z as independent variables. Okay. Now, when you differentiate this partial respect to x, keeping in mind that x and z are independent variable, others are dependent. So, what we will obtain? It is 2x plus 2y into yx, because now y is dependent on x and z, and partial derivative of z with respect to x will be 0 because x and z are independent variables. So, plus 0. Now, from here how can we compute del z by del y? So, y square is z minus x square. Okay. Always first express a variable in terms of independent variables, then compute partial derivatives. Okay. So, what will be yx? It is 2y into yx, which is minus 2x. So, yx will be minus x upon y. So, when you substitute yx as minus x upon y here, so this comes out to be 0. So, values are not same. You see that when we take the first case, value is del w by del x is this thing, and when we take the second case, values are this thing, value is 0, value are not same. So, in the problem it must be clear that which variable we are treating as a dependent variable and which variable we are treating as an independent variables. Now, for the first case, when we are taking x and y as independent variable, we have the notation, and notation is for this, for the first case. For the first case, notation is del w by del x with y. This notation means we are taking x and y as independent variables and others are dependent variables. Okay. For the second case, we take the notation like this, del w by del x with z. This means we are taking x and z as dependent variables and other variables as independent variables. Okay. This is a standard notation. Okay. So, based on this we have some problems. Suppose we have the first problem, we want to solve it. First problem says w is equals to x square plus y minus z, okay, plus sin t, where x plus y equal to t. Okay. Suppose you want to solve the first part, that is del w by del y with x and z. So, what does it mean? It means we are taking x, y and z as independent variable and other two variables which are w and t as dependent variables. Okay. Now, if you want to compute del w by del y, it is respect to y, and we are taking x and y independent. So, this is 0, this is 1, okay. This is independent, so it is 0, and it is cos t into ty. Ty means del t by del y, because t is a dependent variable, t depends on x, y and z. So, this is from here del t by del y is 1. So, it is 1 plus cos t. So, that is how we can solve these problems. Suppose we want to compute del w by del t with xz, fourth part of this problem, okay. Del w by del t with xz. This means we are taking x, t and z as independent variables and w and y as dependent variables. So, how can we find this? With respect to t, you have to differentiate. So, this is so you are taking w and y as dependent variables and x, z and t as independent variables. Now, when you differentiate with respect to t, so x and t are independent, so it is 0. Y is not independent of t, so it is del y by del t minus z and t are independent, so it is 0 plus t is of course cos t. Now, how can you compute del t by del y by del t? You first from this expression you write y in terms of independent variables, okay. Then you compute del y by del t, which is 1. So, it is 1 plus cos t. So, in the same way we can solve all the parts of this problem, and similarly we can solve the next problem, which is del w by del y with x. That means we are treating x and y as independent and all the variables as dependent variables, and similarly for the second part of the same problem. So, thank you very much.